So this is problem 114 on page 15 of the book Strength of Materials, 4th edition by Andrew Pytel and Ferdinand Singer. So problem number 114, the homogeneous bar ABCD shown in figure P-114 is supported by a cable that runs from A to B around a smooth peg at E, a vertical cable at C, and a smooth inclined surface at D. Determine the mass of the heaviest bar that can be supported if the stress in each cable is limited to 100 megapascal. The area of the cable AB is 250 square millimeters and that of the cable at C is 300 square millimeters. Again, this is on page 15 of the book Strength of Materials, 4th edition by Pytel and Singer. Okay, so we first draw the free body diagram of bar AB. Okay. So this one here is point A. We have point B over here, and point C here, and point D here. So there's a cable supporting A and goes up here to E and then back down here to B. And that cable in the free body diagram will be represented by a tensile force. Let's say this one. We can call that, let's just call that T sub 1. And then that cable will continue to point B. Then we have another tensile force here. But since this is the same cable, we can also call this one T sub 1. And then another cable here at point C. That will be T sub 2. So what are the other forces acting on this bar? So those are the cables. Then we have the reaction at point D. Reaction at point D. So let's call this reaction R. Okay? And that R is 50 degrees from the vertical because our surface is given to be, let's just draw a dashed line here representing the surface. This is 50 degrees from the horizontal. That would mean that our reaction R is 50 degrees from the vertical. Because for small surfaces, the reaction is always normal to the surface. So if that's normal, this is 90 degrees here. So 50, this is also a 90-degree triangle. That means this is 40. So if this is 90, that means this is 50. And another angle given is this one here, 30 degrees. And distance from A to B is 2 meters. By the way, there's still one more force missing here. That will be the weight of the bar. And that will be acting at the middle of the bar. Let's call that force W. So B to C is 2 meters. That means B to this point, let's just call this point point F. Okay. So if that's at the middle, meaning this distance here is 1 meter, this is also 1 meter, and this is given to be 2 meters. So what else are given? We are given the cross-sectional area of the cable AEB. That is 250 millimeters or square millimeters. So let's call that area 1 for T sub 1. So area 1 is 250 square millimeters. Then the area of cable C or cable at point C, let's call that area 2. It's given to be 300 square millimeters. It's also given that the stress in each cable is limited to 100 megapascal. So sigma 1 and sigma 2 are less than or should be less than or equal to 100 megapascal. Okay? So some student would find this one easy because we're given area and stress. That means we can solve for the normal force. These values will easily give us the value of T sub 1 from the stress formula, normal force over area. That means the normal force is just stress times area. So we have stress and the area will get the normal force. That means our normal forces are T sub 1 and T sub 2. So they will be solved using this given here. And then sum up moment at point D, with this already known, W will be solved. Well, that solution is wrong. Okay? Because the stress given here are the allowable stress. So we do not know if both T sub 1 and T sub 2 will reach 100 megapascal. Maybe one of them will reach 100 megapascal. The other one will be less than 100 megapascal. Okay? Therefore, we need a relation between T sub 1 and T sub 2. So we will be able to establish the relation between sigma 1 and sigma 2. So which of the two will reach 100 megapascal? So first we will solve for the reaction R. We can solve reaction R in terms of T sub 1. If we sum up forces horizontal, equate that to 0 for equilibrium, that will be T sub 1 cosine of 30. This is the horizontal component of T sub 1 here. So we use cosine because the horizontal component is adjacent to the reference angle. This one here is going to the left, so that's negative R. Horizontal component will be sine of 50 because it will be opposite the reference angle, equals 0. So our reaction R in terms of T sub 1 is cosine 30 over sine 50 times T sub 1. R is about 1.13 T sub 1. We then sum up moments at point F so that W will not be included in the equation, because at point F, the moment arm for W is 0. So this will not be included in the equation. If we consider clockwise moment as positive, clockwise moments will be created by these forces here, T sub 1 and another T sub 1, counterclockwise T sub 2, and the vertical component of R. So positive T sub 1, the vertical component is T sub 1 sine 30, multiplied by the moment arm of 3. That's for this one. For this, that's T sub 1 times 1. This one is now counterclockwise. That will give you a negative moment, T sub 2 times 1. This will also give a negative moment, R cosine 50 times 3 equals 0. So R is, of course, in terms of T sub 1 is 1.13 T sub 1 times cosine 50 times 3 equals 0. So if we transpose T sub 2 to the right side, it will give us positive T sub 2, and on the left side will be the sum of all these T sub 1 terms here. Sine 30 times 3 plus 1 minus 1.13 times cosine of 50 times 3 is 0.321 times T sub 1. Then going back here, for cable AB, our normal force will be the tension T sub 1 equals sigma 1 times area 1. And for cable at point C, normal force is T sub 2 sigma 2 area 2. We substitute this here, we get 0.321 3 to 1, T sub 1, which is this one, equals T sub 2, which is this. We're also given the areas. So we have 0.321, sigma 1, area 1 is 250, sigma 2, area 2 is 300. So we have sigma 1 equals, in terms of sigma 2, that will be 3.74 of sigma 2. Okay, so we now have the relation between the two stresses, sigma 1 and sigma 2. Let's say, for example, sigma 2 will reach the maximum of 100 megapascal. What will be the stress sigma 1? That's 3.74 times 100, and that's 374 megapascal, which is way over 100 megapascal, which is the limiting stress for all the cables. So this is not possible. Maybe if sigma 1 will reach 100 megapascal, how much will be our sigma 2? Sigma 2, so that will be sigma 1 divided by 3.74. That's 100 over 3.74 equals 26.74 megapascal. So meaning, this cable here at AEB will fail first. It will reach 100 megapascal first. When this reaches 100 megapascal, the stress at cable 2 will just be 26.74. So with these values, our T sub 1 from here is 100, which is this one, times the area of 250, so that's 25,000 newtons. Okay, and T sub 2, which is this one, is this stress, sigma 2, 2674, multiplied by area 300 is 8,021 newtons. And with T sub 1 already known, our R1 is 1.13 times T sub 1, that's 25,000. That will give you 28,250 newtons. Okay, so we have the values for T sub 1, T sub 2, and R. So if we have to find or sum up forces vertical and equate that to 0 for equilibrium, we have the vertical component of T sub 1, that's 25,000. Vertical component is sine 30. Another T sub 1 here, that's another 25,000. Then T sub 2 is also upwards, so plus 8,021 newtons. This one. And the vertical component of R, that's 28,000. This is R, multiplied by what? Cosine of 50. And the only force going downward is W minus W equals 0. So from here, we can solve W. 63,679.75 newtons. The problem is asking for the mass, and 1 newton is equal to 1 kilogram meter per second square. So this unit is also the same as kilogram meter meter per second square. So our mass is just the weight divided by the force of gravity, which is in meters per second squared. So we can cancel meters per second squared. We'll have a value of, or we'll have an answer in terms of kilograms. So that's 63,679.75 divided by 9.81 is 6,491 kilograms, or that's about 6.5 megagrams.